All right, let's talk a little bit about internet connections. Since we're talking about connections, that means we're talking about TCP, the Transmission Control Protocol. If you remember, UDP, our other option, is not based on connections, but based on sending packets to a server. But for these connections with TCP, which is usually what we use when we're communicating over the internet, um, the connection is, for one thing, point to point. It connects one process on the client, so that might be your web browser, for example, to a process on the server. That might be the web server process, for example. Um, Connections are full duplex in that data can go in both directions at the same time. While I am sending a request to the server, I might still be receiving the response to my previous request, for example. And it's reliable, meaning when I send a stream of bytes, for example, from the client to the server, making my request, it will be received by the server in the same order that it was sent. If one of those packets went missing for some reason, it will be resent automatically, and that's handled by the kernel's TCP/IP implementation as well as the network hardware between here and there. So a connection has two endpoints, and the endpoint of a connection is called a socket. So a socket needs to specify two things: the IP address of the host that it's running on, what we saw a couple of videos ago, and a port number. The port number specifies which process, and even more specifically than that, which particular service handled by that process we want to communicate with. It's possible for a single process to handle several ports. For example, a web server might handle port 80 for unencrypted HTTP communications, but also port 443 for encrypted HTTPS communications. Even though those are two different ports, they may be handled by the very same process. So a port is a number that identifies the process or the file descriptor within that process that we're communicating with. And there are two kinds. Well-known ports are the ones that I just gave examples of. Port 80, for example, is the port that is used for web servers. Usually on a server will be running and listening to some particular well-known port. That way, clients will know how to access the server. They know if they want to make a request for HTTP that they should connect to port 80 on that server. Uh, an ephemeral port is one that's automatically assigned by the kernel, and this is typically used for client connections. So the client end of the connection, the client socket, needs a port number so that when the server sends its response back to the client, the kernel can make sure that that response goes to the appropriate process. But the process doesn't really care what its own port number is. So that's assigned automatically by the kernel and then associated with that socket until we close it or connect it somewhere else. So the well-known ports also have names associated with them, and there are many, many of those. Port numbers are 16-bit, meaning we have a total of about 65,536 possible ports. Most of that range of ports is reserved for ephemeral ports, but the well-known ports, there are still hundreds, if not thousands of those. And there is a file on your system that has that mapping. So if we look in Etsy services, this is a list of different names for services. So the Echo service, for example, and the port that it runs on. It's on port 7 TCP. Some of these protocols also have UDP ports associated with them. They're designed to work on both. Other times, they only actually run over TCP, but still reserve the UDP port just so it's not used by something else. So we can see, for example, SSH here runs on port 22 TCP. Telnet runs on port 23 TCP. The name service, DNS, which is called domain here, runs on port 53 of TCP and UDP. DNS requests are usually done over UDP, but it's possible to do them over TCP as well if the server supports it. And we can scroll through this and find other things like HTTP, runs on port 80. It's also known as www. And scrolling through, we can see there are a lot of things here. So on our particular computer, the ones that are listed here go up to about 20,000, meaning everything above that is available for ephemeral ports. Although there are some services that use even higher numbered ports. The kernel will make sure that if it does assign an ephemeral port, that's not associated with the same port number as the service that is actually running on this computer. If I don't have a FIDO server, and I probably don't, then it's okay for the ephemeral port number 60179 to be used. But if I am running this server, then of course it shouldn't be used, so that it's that port is reserved for that server. So a connection then has two sockets associated with it, the client socket and the server socket. And each of those sockets has an address that is the IP address of that client, for example, and the port number on the client. Again, on the client, that's usually an ephemeral port number, usually a large number. And on the server side, we have a server IP address and the server port number, which here is 80, which is one of those well-known services. So the connection itself can be identified by that pair. I can't have two connections on the internet with the same client address, client port number, server address, and server port number. So what do I do if I want to, on my computer, make two different connections to the same web server? Let's say that I've got a browser open and I'm looking at Reddit, and I have my incoming messages open in one tab and the homepage open in another tab. Those are both connecting to the same server, reddit.com, and the same port 443 for HTTPS. They have the same client IP address, because my computer has one IP address usually, but they will have different client port numbers, because each time I make a new connection, even if it's to the same server, I'll get a new ephemeral port on the client. So when my client sends out a request for, let's say, this IP address, port 80, the web server on this address, that computer is probably running several servers. So the web server is one process, the echo server is in another process, there might be a mail server running in another process. The kernel looks at the port number, the server port number or the remote port number, the one that we're trying to connect to, and the kernel has a table that says port 80 belongs to this particular process, actually saying that port 80 is associated with this particular file descriptor in this particular process. So then the kernel can send that information along to that file descriptor, and the server, as it's doing things with that file descriptor, reading from it, or we'll see in a later video, listening for new connections and so on, can receive that information and make the connection as appropriate. If the client sends a request to a different service on the same server, then the kernel, again, in its table, is able to figure out what process and what file descriptor that is and pass the information along to the other server. So we do this using something called the sockets interface. So this is a set of system level functions. So it's a combination of library functions and system calls used to build network applications. The sockets interface has been around since the early 80s. It was part of the Berkeley distribution of Unix, which was one of the first Unix distributions to support to support the internet. Um, Berkeley, by the way, that's a university, the University of California, Berkeley. But Berkeley Unix, you might have heard with a different name. If you've ever heard of BSD, that stands for Berkeley System Distribution. That is Berkeley's version of Unix. BSD and AT&T's System 5 were in the 80s and 90s the two main versions of Unix, and most versions of Unix since then have been based on one or the other. Linux is a little bit different. Linux isn't based on either BSD or System 5, but it is its own from scratch implementation that tries to implement the good parts of both BSD and System 5. Operating systems based on BSD, though, you probably encountered some because Mac OS is based on BSD. You might also have heard of FreeBSD and OpenBSD and NetBSD, which are distributions of Unix based on the original BSD distribution. Pretty much all modern operating systems use the same sockets interface, even things that aren't based on Unix. So Windows, for example, has socket functions that are very, very similar to the ones we're talking about here. In early versions of Windows, I'm thinking Windows 3.1, for example. This was in the mid to late 90s. The TCP/IP interface was provided by a separate program that you would run. There was some program called WinSock that handles TCP/IP communications. With later versions of Windows, that was integrated into the operating system. Other things like Mac OS or Linux have supported TCP/IP from the very beginning. When I say very beginning for Mac OS, I mean OS 10. There were earlier versions of Mac OS that weren't Unix based that had more or less internet support depending on when they were released. All right, so what about a socket? So we said that a connection is identified by socket addresses, but what is the socket itself? So on your computer, a socket that you have is the endpoint of a communication, and that's how the kernel thinks of it. But to your application, to your web browser, for example, or to your mail client, a socket is a file descriptor. When you write to that file descriptor, it sends something to the socket, the other end of that connection, the socket on the server. When you read something, it waits for data to come in from the server being sent back to you. And as usual on Unix, input-output is always modeled as files. So we have this file descriptor, we could write bytes to it, we could read bytes from it, just like we could with a file. And fortunately, connections over TCP/IP are modeled as a sequence of bytes, just like a file. So the client will have one file descriptor for that connection, or for its end of that connection. The server will have a file descriptor for its end of the connection. Anything the client writes to its file descriptor, the server will get when it reads from its descriptor, and vice versa. So the main difference between these network file descriptors, these sockets, and file descriptors referring to regular files or to pipes or to devices like the terminal on your computer. The main difference is how we open them. We can't just open a particular file with open because we have to specify several things: where we want to connect to, the IP address and the port number of the other end of the connection. We have to get an ephemeral port assigned to us. We have to actually initiate the connection so the server knows that we're talking to it, and so on. So there are a few different data structures related to this. The most general kind is this struct sock adder. And you'll notice that it has some information associated with it. It has an SA family and it has this 14-byte character array, but it doesn't have the stuff that we would expect. It doesn't have a field for the uh, IP address. It doesn't have a field for the port number, and so on. Now the reason for that is the socket API, the set of system calls and functions for handling sockets, can handle more than just TCP/IP, more than just the internet. They can handle different kind of networking protocols. Some of those are obsolete, some are still in use. Um, so when we refer to a socket address, this is the kind of thing that we would pass into one of the functions. But if we want to actually fill out information in it about what the what the IP address, what the port number, and so on is, we need a more specific structure. And we do that with one of a variety of structures. Which one we use depends on the particular kind of connection we're making. Is it over the internet? Is it TCP? Is it IP? And so on. So this is one called sockEdr IN here for internet. So this is how we specify the address that we're connecting to, also our local address for our socket, our end of the connection. So we have a family for internet connections that's always AF INET. AF here stands for address family, and INET for internet. Then we have the port number, which is 16 bits. We have the address, which is that struct IN adder we saw before, but essentially a 32-bit number. And then we have enough padding to fill it out to the size of a struct sock adder. Struct sock adder is bigger than we need for an internet IPv4 address, but because some other protocols have longer addresses or longer port numbers or additional information, and because the functions that we call are going to be looking at the full, as we can see here, 16 bits plus, or 16 bits, 2 bytes plus another 14 bytes, 16 bytes. Because those functions expect 16 bytes, we need to make sure that we have additional padding to make our struct fill out that full 16 bytes. For some protocols like IPv6, struct sock adder actually isn't big enough. This isn't big enough to hold an IPv6 address. And we'll see later there are some things we can do to handle that. All right, so here's the general sequence of what happens when we're making a connection. And this is happening on two sides, the client side and the server side. And they are doing different things to set up the connection. Once we're connected, they're going to do more or less the same thing, write and read. The functions referred to here, RIO write in, RIO read line B, these are not standard functions. These are provided for you in the csapp.c file. Those are the wrapper and other helper functions provided as part of the textbook. In an application that's not using those, you might use the write system call and the read system call, for example. These versions give you a little more flexibility, handle some of the things for you, so that you don't have to worry about all of the details. But for connecting anyway, we start out by doing get adder info, because we probably, for the server, have something like a domain name, www.cs.uky.edu. Or maybe we have an IP address, but that was probably written as text. Someone typed in 128.163.48.21. So get adder info will take that and produce a struct sock adder that encodes that information. Also, the port numbers there. So when we ask for the address, we might say, I want to talk to the service www or HTTP on www.cs.uky.edu. Get adder info turns that into a struct sock adder. Then we can call the socket function to create a socket, to create our endpoint of that connection. Then we call the connect function. We provide it with the information we got from get adder info about the server to say who we want to connect to. Once our connection happens, once we get something back from the server saying, okay, you're connected, then we can do a sequence of writes and reads, whatever our protocol demands. And then eventually, when we're finished, we'll close the connection or close our socket, which will end the connection. It will send an end of file to the server, which can handle that. On the server side, it's a little bit different. We have a few extra functions we have to call. We still start out with the get attr info. Now, this is a server looking up the information about itself. If I'm writing a web server, for example, it would look up HTTPS and maybe one of this machine's IP address. A single computer can have several IP addresses. One is most common, or one publicly facing IP address is most common, but it's possible to have multiple ones. Get attr info lets us specify which IP address we want to listen to. Then we call socket to create that, to create the file descriptor. We call bind to associate the socket with a particular port on the server. So bind is what we would use to say, now that I have my socket, I want it to be associated with port 80. Then we call listen, which says wait for connections to come in. When a connection does come in, the server will be notified about that and can call the accept system call, which accepts the connection from the client. Now that's going to give us a separate file descriptor because we still want to be able to listen for more connections to come in while we're handling this client. How we do that, we'll talk about later. That might be with multiple processes. It might be that we just don't wait for any more connections until we've handled this one, if it's a very short-running service or one that's easy to send a response to while we don't have to wait very long. We could even do it with multiple threads within the same process. But once we've done accept, we have a connection between the client and the server. So the server might, for example, do a read, which is waiting for the client to write something. Once it gets that read, it might write back a request to the client, which hopefully the client will read, and we repeat that process. Eventually, when the client closes the connection, the server, when it does its read, will get an end of file. When the server gets an end of file, it can close the connection, and since the client has already closed it, we've now terminated the connection. All right, so you'll also notice here there are a couple of functions listed: open client FD, open listen FD. These are, again, things that are provided for you in the CSAPP library that handle the most common cases of doing things like this in the client, doing the get attr info, creating the socket and connecting it. Or on the server end, doing get attr info, creating the socket, binding it to that port and IP address, and listening. You can also implement those by hand, and if you read the code for them, you'll see that they do exactly this sequence of system calls. All right, so the first of these, get attr info, lets you, as I said, convert between host names or IP addresses written as strings into numeric addresses of the kind that would go into a struct sockattr. There are some older functions like get host by name and get serve by name that do part of this, but have some more restrictions or a little bit harder to use. So those are obsolete. We typically wouldn't use them anymore. One nice thing about get attr info is that it's protocol independent. If this particular server has an IPv6 address rather than an IPv4 address, then this will set up an IPv6 address. We can even specify which of those we want if we have a server that supports both. Get attr info is pretty complicated. Fortunately, there are just a few different usage patterns that will handle most of the cases you need, hence those wrapper functions provided in the CSAPP library. So get attr info, you can look at the man page for it for more information, but it takes several things. It takes the address of the host, either a domain name or an IP address written as a string in that dotted quad format. The service, either as a name like HTTP or HTTPS, or as a string port number if that's what the user specified. We can have some hints which tell getAddrInfo what kind of stuff am I interested in. We don't necessarily use this a lot, but occasionally. And then a pointer to a pointer. So this, so we will have a variable that is a struct attrinfo star that will hold a pointer. We would initialize it to null, pass in the address of that pointer, so a pointer to a pointer, and then getAddrInfo will store a pointer that points to a linked list that has the information about that address. And why is it a linked list? Well, a single address, as we saw with the Twitter example when we were looking at DNS, a single domain name might have multiple IP addresses associated with it. Potentially, a single service could have multiple port numbers associated with it. So this will return a list of all the possible ways to connect. And usually in the client, we'll go through that list and try them one at a time until one of them works. Now, since we've got a linked list, which is a pretty complex data structure, we also have a function that will free that linked list. So we don't have to go through by hand and delete or call free on each node in turn. That linked list that's returned will have a collection of entries. An entry will have maybe a canonical name. It will have an address, which points to a struct sockattr, and it will have a next pointer, which points to the next entry that we got from attrinfo, and so on. Eventually, one of the next pointers will be null. That's how we know we've reached the end of the list. So a client, when it gets this list back, will go through one at a time and try this first address, try to make a connection. If that fails, then rather than saying I couldn't connect, it will go to the next address that was returned and try that. If that fails, it will go to the next one, and so on. So the client's attempt to make a connection, we only really consider that to be a failure if we've gone through all of the attrinfos that we got from getAddrInfo and none of them worked. On the server, we do something similar. We try making a socket and binding it to this attrinfo. If that didn't work, we'll go on to the next one, try binding it to that. Sometimes on the server, we will bind all of these because we want to listen on every possible address for this service. If that happens, then we do have to do some more work to make sure that we're listening to all of those different services. We might do that with one process per attrinfo by calling fork as many times as we need to. We might do that in separate threads. Or there's a system call called select, which allows us to do multiplex communication. With select, you can say wait until something happens on any of these file descriptors, where here the file descriptors will be sockets. And again, more information about the attrinfo struct. You can see more about this by doing man get attrinfo. So I'm not going to talk in detail about all of those. But the struct sockattr here, this is the important part. This is the thing that we're going to pass to connect and to bind. The other things are also useful. We will need those for some of the socket functions that we're using. Then there is something called getNameInfo, which is the reverse of that. We give it a struct sockattr and some additional information associated with that. In particular, it needs to know the length of that sockattr because some types of address like IPv6 are bigger than a plain struct sockattr. And it will give us back some out parameters. The host name, we have to specify the length of the buffer that we want the host name to be stored in. The service name, And again, we need to specify the length of that buffer so that we don't have a buffer overflow. And then we might specify flags to get name info, asking, for example, to say whether I want to get the name back as a domain name, www.cs.uky.edu, or as a string representation of the IP address, 128.163.48.28. So there is an example. You can find this in the lecture 16 code about how to use get adder info and get name info. Now you'll notice this uses get name info with a capital G. That's a wrapper function provided by the CSAPP library. Likewise, free adder info is a wrapper function, and these wrapper functions are there to handle errors. If there's an error, it will report the error message and then terminate the program. All right, and if you run this, you can give it a host name, and it will return the IP address. If you give it a host name that has multiple IP addresses, like twitter.com, then remember get adder info returns a linked list. This will go through that linked list and translate that struct sock adder into a string and print out that information. So notice that string, we pass in a buffer. We also have to say the length of the buffer, in this case max line, which is defined in csapp.h, and it will write as much of it as it can to the buffer, being careful not to overflow as long as we specify the right length, and then we'll print it out. So you can test that host info program in the lecture 6 code, try running it, and hopefully find some interesting stuff out. So that's all for today. In the next set of videos, I'll talk in a little more detail about network programming, about the sequence of system calls we need to make, how to call them, and so on. But that's all for today. Thanks a lot for listening.